Okay, I think we can get started. Welcome everyone to this new Datadog episode. If you don't know Datadog is a series of live streams where we invite engineers working every day on building Datadog itself to talk about something that they're working on, something that they're solving, a specific technology, anything. All of these episodes are always recorded, and they will be available on Datadog on .datadoghq.com. So if you want to see any of the previous episodes, or you want to pass this one along to your colleagues, this one will be available in a couple of days, depending on our video team, but hopefully very, very soon. And any of the previous episodes are already available there. Today, the topic that we chose today is how we manage auto-scaling in our Kubernetes clusters. And the best thing about this episode is that you can ask as many questions that you may have at the end. We have here two very high-level Kubernetes engineers who know a lot about it. So if you have any questions, the thing that you need to do is to press the Q&A button that you have on your Zoom webinar and leave the question there, and we will go back to those at the very end. Same thing, if you're in LinkedIn, leave a comment and we will answer those questions there as well. So again, on this episode, what we talk about is how we build Datadog internally. But just so you know, Datadog is a platform that helps companies improve observability and security of their infra and applications, including, of course, Kubernetes as a platform, but also the applications that you run on top. We are heavy users ourselves at Datadog of the Datadog platform, so obviously it's a little bit meta, but we use Datadog a lot to solve the same problems that you're solving every day. My name is Ara Pulido. I'm one of the co-hosts and co-organizers of the series. So if you have any feedback about the series, or if you want to propose a topic or anything, please do reach out. But the important people today that we have here today are Corentin and Charly. Corentin, do you want to introduce yourself?
Sure. Hello, everybody. I'm Corentin. I'm working on the Vivant platform. I joined Datadog five years ago. And over the last years, I mostly worked on integrating our internal application to Kubernetes the best we can, including obviously autoscaling and a bunch of other things.
Fantastic. And Charly?
Hi, everyone. My name is Charly. I joined Datadog 8 years ago. I'm the engineering manager for a team called Container Ecosystems, and we own the open source tooling to deploy our open source agent in orchestrated environments like Kubernetes or ECS. And we also own the autoscaling at the pod level, which I'm excited to talk about today.
Fantastic. Thank you. So just to start, one of the things that we always do is to give you a little bit of an idea of the Datadog scale, basically because some of the solutions and some of the decisions that we make in our engineering infrastructure are related to this. So Datadog has more than 25,000 customers, and we are an observability platform, so we are collecting telemetry from all those customers, and those ads collecting telemetry from millions of hosts. That translates of tens of trillions of data points per day that we need to ingest and we need to process. And we run all of this in Kubernetes ourselves. So Datadog's Kubernetes infrastructure is a very large Kubernetes infrastructure. We have thousands of clusters, some of them with more than 1,000 nodes. That basically translates into hundreds of thousands of pods running every day at every moment. And we run those on different clouds. So we are on different public clouds, all of them running on Kubernetes. And the thing that we are going to be talking about today is autoscaling. And the first thing before Corentin and Charly start, I think it's important to understand what we mean by autoscaling in general in Kubernetes, because we could be talking about cluster autoscaling, horizontal pod autoscaling, and vertical pod autoscaling. These are the most common ones. And the thing is that at Datadog, we are using the three of them. So we are using cluster autoscaling, which in a nutshell, is increasing or decreasing the number of nodes in your clusters. We are also using horizontal pod autoscaling, as Charlie mentioned, which basically means increasing and decreasing the number of pods in your workloads. But also we are using vertical pod autoscaling, which even though it's a Kubernetes project, it's less used, as we saw on the container report at Datadog. It's less used, commonly used. So let's start by cluster autoscaling. And we are going to be covering all these three. And actually, cluster autoscaling, we already talked briefly about it on a previous episode of Datadog on, more specifically talking about node management at Datadog. So if you want to know more about how we manage nodes at Datadog in general, please go and check that recording. But to give you a recap, Charlie is going to explain us a little bit cluster autoscaling in Kubernetes, and more importantly, how we use it here at Datadog.
Right. So the cluster autoscaler is the first resource that we'll be talking about. And as you said, it's not the one we'll be spending most time on. It is a resource that's developed and maintained by the special interest group on autoscaling from the Kubernetes community. So it's an open source component, and its main goal is to manage an elastic fleet of nodes, scaling up to cope with the demand and trying to get rid of unused nodes. And we're actively contributing to this project since, as you said, we use it a lot internally. So at a high level, it does the bridge between the Kubernetes cluster and the cloud provider's instances and resources. It can run in many cloud providers, and it needs to interface with what we call node groups. And these are specific to each provider. So for instance, in AWS, you have the autoscaling groups. In GCP, you have the managed instance groups. And in Azure, you have the virtual machine scale sets. And as many of you know, Datadog runs in all three cloud providers. And so in order to best scale the node groups we have internally, we developed an abstraction called Datadog Node Group. So for application developers, they can create their Datadog Node Group and configure their applications to target them. And more recently, we even went further and abstracted this away more so that application developers only need to configure the pods that they want to run, and the internal infrastructure team takes care of the underlying infrastructure entirely. Now, getting into the weeds a bit, the first main task that the cluster autoscaler fulfills is the scale-up of node groups. It's very straightforward. When you create a workload, like a deployment, or if new replicas are added, the kube scheduler, which is part of the Kubernetes control plane, will schedule the pods. However, they may end up as pending because they can't find any slot on a given node. This could be because of taints, could be because of affinity, or could be because there is no room. And so when that happens, the cluster autoscaler watches for these specific scenario. We will request the creation of a new node that matches the requirement of the pod, and that will provision a node from the node group template from the cloud provider. Once the node is ready, the kube scheduler will be able to bind the pod on the new node. And as the workload gets scheduled, hopefully everything runs correctly. Now, the opposite version of the scale up is the scale down. When a node is empty, we don't want to pay for it, obviously, and the cluster autoscaler watches for empty nodes. When it finds one, it adds a taint to the node that it wants to downscale, and then that terminates the node. Now, the last feature available I want to discuss today is repacking. In the cluster autoscaler, you can configure a utilization threshold for a node. If the usage is below that threshold, the cluster autoscaler will start doing rescheduling simulations. And if it finds that the pod can be running, that is running on the underused machine can run elsewhere without scaling up, then it starts evicting the pods, and the node, which was underutilized, end up being empty and therefore scaled down.
Cool. Very, very interesting, and definitely recommendation to start using repacking if you don't do already, because it's a very easy way to save cloud costs, to basically repack everything in a more efficient way. So now we are going to be talking about horizontal pod autoscaling, and this is probably where we are going to be spending more time. This is the most popular form of autoscaling in Kubernetes. As I mentioned at the beginning, we run a container, what we call a container report every year, where we collect data from our customers who are running containers. And one of the things that we saw on the latest report is that half of our customers that are running containers in Kubernetes are actually using the HPA. So very, very popular. And we ourselves at Datadog, we are heavy users of the horizontal pod autoscaling in general. With a tweak, we use it with some extensions that Charly is going to discuss as well. So Charly, do you want to give us first an introduction of HPA in general, but then how we use it here at Datadog?
For sure. So the popular out-of-the-box controller, rightfully called horizontal pod autoscaler, it runs in the control plane alongside other controllers like the deployment controller and others. And its core feature is the ability to control how you want to scale a target that can be a deployment or stateful set using a threshold and just a metric. It can use multiple types of metrics, such as resource metrics like CPU or memory. And as you can see in the example on the right of the slide, as well as external, which are coming from outside the cluster. More on that later. But the basic use case is to have a HPA based on a resource metric, and these metrics that are sourced by a component called the metrics server. The metrics server is an open source project, which is also supported by the Kubernetes community. And unfortunately, it does not scale well for very large clusters. And per the documentation, it's best suited for clusters of up to 100 nodes. And so over the years, the HPA controller has been supporting more and more features, allowing users to control with granular configuration how their workloads are scaled. Besides the various types of metrics I mentioned earlier, one can specify the initialization period or a readiness delay, as well as policies to have a scaling decision only happen if a condition is met for a certain duration. And so, as I mentioned earlier, there is another type of metric that is available, the external one, which are supported by an external metrics server. And this is the one that we use at Datadog. It works similarly as the regular metrics server in the way that is registered as an API service route, which is registered in the API server. However, there is no common provider backed by the community, so it's up to the user to implement their own. The benefit of the external metrics provider lies in its flexibility for the metric. You're not restricted to a resource such as CPU or memory. You can use any arbitrary metric name and labels so long as the external metrics provider can return the value when it's queried by the HPA controller. And so we decided to implement our own external metric provider, which runs in the Datadog cluster agent in our implementation. And we try to make it as user-friendly as possible. As such, when one creates an HPA object, the cluster agent will receive an event containing the HPA spec, and we will extract the metric name, the labels that are desired. And we query our metrics backend regularly so that we can serve the value retrieved when the HPA controller reconciles an HPA object. and asks for the value to compare to the threshold. If you have many HPAs and therefore many metrics, the cluster autoscaler will batch the queries and ensure the freshness of the values prior to serving them. And for our customers who want to autoscale their workloads using this model, it's the exact same experience. Whether you deploy with Helm or the Datadog operator, you have the option to enable this feature in the cluster agent, and everything is done automatically for you. But we faced somewhat of a limitation with the HPA definition. The HPA spec only allows you a basic metric name for external metrics. And usually you would like to drive your scaling events with complex queries. Technically, it's a field that needs to pass the RFC 1123, which historically defines the requirement for the internet host software, which restricts only to lowercase characters with dash and dot. But it cannot contain curly brackets and other symbols that we are making use of in the platform for complex queries. And as I said, when you're in Datadog and you watch your dashboards and such, you need to make the complex queries. So let me walk you through how we solved this. We created another custom resource called the Datadog metric. It is reconciled alongside the HPA in the Datadog cluster agent, and it puts the external metric as a first-class citizen in the cluster. A typical Datadog metric will contain the query to use and be referenced in one or multiple HPAs. This framework allows us to do a lot of cool things. For instance, we have a much more informed status on the value. When was it last updated? What is the timestamp of the value? Are there errors? And so forth. And when the controller is enabled in the cluster agent, we auto-generate Datadog metric objects for all the HPAs. But more importantly, the query field is much more flexible, allowing you to effectively copy-paste queries that you use in your Datadog dashboards to effectively scale on what you see. And in the end, they also allow users to potentially improve the lifecycle of their own controllers, since the object can be used as a new data source across the cluster.
Very cool. I have to say that when I started doing autoscaling in Datadog, the Datadog metric is something that I always liked. It's a very good example of a very, very simple solution that works very, very well. Simple from a user point of view. So let's now talk about those tweaks that I mentioned at the beginning. So we use a lot of what we call horizontal pod autoscaling, which is increasing, decreasing replicas, but we use it using something called the Watermark Pod Autoscaler. And Charly, you're one of the main contributors of the WPA. So what it is exactly, and why did you decide to build it?
Right. So you're right. This is what we're using internally, and I want to talk about what it does in detail. But essentially, we created this new controller to circumvent limitations in the HPA controller itself. The initial premise was very simple. HPA has a single threshold, which leads to sawtooth patterns, which it's less than ideal for a real-life autoscaling lifecycle. So we started investigating how could we have two thresholds that would define a stable regime in between and have it in a dedicated controller. And also, what other features were we missing? So we started by implementing all the features in the HPA controller, with behavior policies. We included the stabilization windows, the velocity limiters, along with our watermarks. Now, it's worth noting that in the HPA, you can specify a toleration, which is by default, I think, 10%, but it is at the controller level. So it's applied to all the HPA objects. And as we introduced this new pattern, the adoption picked up. And so we started introducing new features like a dry run mode to help with confidence for people that deploy the WPA and have the metrics showing the replica proposal and how each filter would affect the scaling decision without making the decision. More recently, we introduced the modular scaling for workloads that work in high availability mode and need to scale by 3 or by 5. The scaling delay to avoid scaling on bursts, and finally, converging in stable regime. One of the main benefits of the WPA is that it's an isolated controller. So we can very quickly iterate and have a much smaller impact on the full control plane. So that's the one feature that I want to talk about specifically. One of the newest features is the ability to converge towards a watermark in stable regime. In the graph that you see here, we have a high watermark of 65, a low watermark of 45. They likely represent a CPU usage. And there is a 20% difference, meaning that no scaling will be recommended whether you run at 46% or 64%, regardless of the number of replicas. For workloads with a few replica, this is not a big concern because adding or removing a replica when you are between the watermark would probably lead to instability. However, when you have tens or hundreds of replicas, this could represent up to 20% waste. So we added the ability to run simulations to slowly remove replicas to converge towards the high watermark, or add replicas to converge towards the low watermark. And when we started rolling out this feature for large teams internally, we saw that the savings were significant. As you can see in the graph here, we're showing the number of events per CPU. The blue time series is the current utilization compared to the gray time series, which is time shifted by a week. And this represents, in this case, more than a 10% optimization. Now, all is not green, but pink and rosy, but there are some lessons learned. And I think my favorite one is just to revisit metrics and watermarks regularly, because what might work today is not valid tomorrow necessarily. And make sure that you alert when you reach the maximum number of replicas or the minimum number of replicas. Another one could be to educate the developers so that they understand how it works. And especially during incidents, you need everyone to understand the life cycle so that they can take the right actions and move the WPAs in dry run, for instance, and make the best of this controller.
Cool, thank you. Thanks for that overview of the Watermark Pod Autoscaler. By the way, WPA is an open source project. It's on the GitHub organization for Datadog. So if you haven't tried before, you can just download the controller and give it a try on your staging environment. And of course, leave your GitHub issues and comments if you have any questions. So let's now move on to best practices that we learned over the years for horizontal scaling. We are going to go through some of the things that we've learned that work well for us. And this is important to notice. These are things that worked very well for our environment. Some of them may work for you as well. Some of them may not. So something to take into account. This is not one size fits all, but at least this is what worked for us. So Corentin is going to go through some of the things that we learned over the years. And we are going to start by one that may maybe surprise people, is that what signals to scale, to drive all these scaling events to choose. Because some people think, okay, I'm going to use things like the fork on those signals. For us, something a lot simpler is what works.
Yeah, exactly. Like the first thing that you want to look at when you configure your autoscaling, your horizontal autoscaling, is the metric that will drive the scaling. And often people want to look at latency because they are like, okay, my service is slow. When it's slow, I want to add more resources because it's going to make it faster. The thing is that often it's not true, right? If you have a web server and your service is slow because the database is slow, adding more web servers is not going to do anything. And while it works sometimes, it often leads to inefficiencies. So we found that as a basic rule, we will try as much as possible to use low-level signals like raw resource usage to drive autoscaling. And most of the time, it happens to be CPU that is driving that, because with what we do at Datadog, most of the things are CPU bound. This means that there is often some work to be done on the application to make sure that performances are not degrading until you reach at least 80 or 90% of the available CPU. But once you have that, it becomes very easy to understand how your autoscaling is working. For a CPU bound application, you will want to use the CPU as a percentage. Unfortunately, it's not available yet as a metric. You need to divide the CPU usage by the Kubernetes request to compute it, which you can do in a Datadog metric. But in the next months, we are going to provide a normalized CPU usage distribution, meaning that it will be a simple metric to query, plus you will be able to use percentile instead of only averages. The next thing that you want to do once you have a good metric to look at is to define the watermarks that will trigger the scale up and scale downs. Assuming a standard deployment on 3 failure domains or ISIs with a minimum amount of replicas of 3, this is, I think, what you will want to use. A low watermark of 40% and a high watermark of 65%. Why these magic numbers? First, they allow you to lose a full AZ with no impact. Losing a full AZ, you will lose a third of your replicas, which is exactly what is above 65, kind of. It's also what you would lose if you lose a single pod when you have the minimum amount of pod. Plus, if you go from 3 to 4, you would add 25% of capacity, which is exactly the difference between 65 and 40. Obviously, here the difference between low and high is pretty high. So if you want to optimize further, you will want to set the convert to watermark feature to high watermark. Once you have watermarks, you probably have like scaling that is working pretty well, but you maybe want to optimize cooldown to make sure that first, you don't scale up too fast when you have a short burst of traffic, and second, you don't downscale while you could keep the capacity for a while to absorb the next predictable burst of traffic. So it really depends on the periodicity of traffic. We found that for workloads that could have a few seconds of latency, and it will be okay to scale down every hour. While for workloads that cannot afford to get more than 1 second of latency and have a daily periodicity, we would wait up to 3 days to downscale, because weekends the traffic is very different. We might have a bank holiday on a Monday, so 3 days is a good number. So you really need to look at your traffic, to look at simulations, which is why it's interesting to have the driver mode, and then to set up the cooldown as you like. Once you have all of these, you go into you get into more complicated things to handle. A critical component to think about when you have autoscaling is the load balancer. You're adding more pods, so you need something that is spreading the load across these pods. And if the load isn't balanced, you will have poor results. Why? With an unbalanced load, if you look at the average resource usage, a few overloaded pods will not trigger an upscale, and even though the service will be degraded, the number of pods will stay constant, which is not what you want. A quick fix when you see that will be to set it to the max, but then a single misbehaving pod could lead to an infinite scale-up, also probably not what you want. Using a distribution is a potential solution there. You could use the P75, for example, and a few pods with higher traffic would lead to upscales, but that would also lead to unused resources. Both components, load balancing and autoscaling, really go hand in hand. And for an optimal use of resources, your load balancer needs to spread the loads evenly across all pods. And it's important to spread the load on the traffic across all pods. What does that mean? For example, last year, we moved part of our infrastructure to ARM, and these machines have very different performance profile than the ones that we were using before. And we had to make sure that the load balancer will account for the actual load that it was seeing and not just try to simply spread the traffic. Otherwise, we would clearly see imbalances between the old and new kind of machines. A way to do that, for example, if you use gRPC, is to use weighted round robin load balancing, where the application will periodically report its load to the client, and the client will lose the load to compute a weight to do weighted round robin. If the traffic is still unbalanced, you can use a CPU usage distribution, as I said earlier, instead of an average. But again, do not use the max. So we explained what you can do for simple CPU-bound applications, and I think for most applications that works pretty well. But when you're working with a proxy, reverse proxy, load balancer, that kind of thing, which you also want to autoscale, it becomes more complicated. You often are bound by different kind of resources. It might be CPU or network, depending on the kind of traffic that you have. And in this case, you want to use both of these metrics as your signal. Well, the WPA has the option to look at multiple metrics. We found that it was not the most optimal way to do that. Instead, the suggestion here will be to export the composed metric that is built from both or multiple kind of loads, and use that in the WPA, or try to craft a query, a single query in a single data metric that look at everything that you want to look at. Another option is to have a third-party jobs that will read the simple metrics that you have from Datadog and periodically re-export a composite metric made of all of them to Datadog again. A few slides before, we talked about failure domains or AZs, and it's really important to make sure that we reduce the impact of losing one failure domain. And for that, you need to make sure that you configure the load balancer to spread the traffic evenly, but you cannot only rely on that to have the correct number of pods in each AZ. And a common mistake is to say, okay, I want 1/3 in this AZ, 1/3 in this AZ, and 1/3 in this AZ for the traffic, and I will let the autoscaler do that. But that doesn't really work. You could have issues where one AZ cannot scale up anymore. The load balancer won't know, it will still send 1/3 of the traffic, and one AZ will have degraded performances. Instead, what we advise is to make the load balancer look at all the pods as a single pool, and then try to bias the way that you upscale and downscale in each of the zones by looking both at the global utilization, but also at the number of pods in the local zone and at the number of pods in the entire region. And if you have less pods in the local zone, try to increase a bit the load artificially. If you have more pods, decrease it a bit, and this will automatically balance the number of pods in each one. You can do that by simply doing a quite complex query in Datadog metrics, where you would multiply the observed signal with the number of local pods divided by the number of global pods, for example.
Cool. Thanks, Corentin, for those best practices. Just so people know, these practices come from many years of trying things, doing experiments, and this is still happening. So Datadog continues to do these experimentations on how to improve. how we autoscale. So this is not an easy thing. It takes a lot of trial and error, but we will continue trying to improve it. So moving to from horizontal to vertical, and vertical pod autoscaling, as we mentioned, is about requesting the number of resources that you want for the containers on your pods. And this is something that is actually a lot less used in the community, basically because it's kind of not easy. But it's still very important to get it and to get it right. And why is this important, Corentin?
Sure. So why do we need to care about sizing pods? A pod is a container. It's where your application run, and your application cannot use more resources than you gave to the container. Think about gaming. Like if you try to run the latest games on a machine that is like from 20 years ago, it's probably not even going to start. If you're running Tetris on the latest gaming laptop that you can buy, sure, it's going to run pretty well, but it's not super efficient and probably not a good use of your money. It's exactly the same thing here. If your pods are too small, you will have performance issues, be home killed, and probably not even start. And if you size them too big, sure, it will work well, but you will waste a lot of money and energy. A good question is, what are the optimal values? If you run a single pod, sure, you can look at the historical usage, tweak it, and you're done. But often if you run Kubernetes, it's not to run a single pod. It's because you have like hundreds of them, thousands of them across hundreds of microservices. And hand tweaking all of them by hand would be very time consuming. What's the proper size for today, for next week, for next month? There is Black Friday coming. What should we do? What's the proper size in staging and production? Maybe you have clusters that are dedicated to single customers, test clusters, whatever, you're sharding your applications. So that's really would demultiply the possible configurations, and it becomes impossible to do all of this by hand. The official solutions for that is the vertical pod autoscaler. It's a controller made of 3 different parts. The first one will be the VPA recommender, which will look at metrics for specific deployments and provide recommendation based on historical usage. The second one is the updater. It's going to look at running pods, see if their current resource allocation differs from the recommendation, and if it does, and if you have the right update mode, it's going to restart them. And while they're restarted, they are going to go through the admission. And during the admission is going to fetch the latest recommendation and apply it to the newly created pod. You can configure the VPA recommender. The default one, which is provided upstream, will simply use for all the applications the P95 of CPU and memory over the past 8 days. And because this was too strict for us, it was not possible at Datadog to have a setting for every application, we came up with the Datadog recommender, which instead allows you to configure which percentile you want for CPU and memory, and has a lot of other options that we are going to describe a bit later. It can also look at external metrics, such as Datadog metrics. So what are the other Datadog recommender features? It's optimized for Datadog, so it's going to use the API efficiently to reduce the number of queries that we do to the backend in order to make sure that we don't rate limit ourselves. It also has additional post-processors, which are like bytes of codes that are run just after you fetch the metrics. For example, you can have a resource ratio where you define the number of gigabytes of memory you want per CPU, a safety margin, replica counts restrictions for cooperation with WPA. We're going to look at that a bit further. And more interestingly, it can allow you to craft your own query by hand, like the WPA, using Datadog metrics. And that's actually quite interesting. For example, if you have an application that has leader election, you want to size the non-leader pods to the size of the leader that currently has traffic, because when they become leader, you want them to have the same resource allocation. So the Datadog recommender with its default behavior will look at P55 on the peak memory usage for the past 8 days for the active VPAs. And the users can also configure the percentile or the window of time using simple applications, simple annotations in their VPA configuration. When using external metrics, instead of doing queries to Datadog directly, it queries the external metric, the Datadog metric that we saw earlier with the WPA, which you will need to write yourself. And that allows you to write exactly the query that you want to do for this specific application. Why do you need a configurable rolling window? It really depends on the periodicity of traffic that you have with your application. The default 8 days window is pretty good if you have a daily or weekly periodicity. And again, you have 8 days because you might have a bank holiday on a Monday. But it's not necessarily a good fit for every application. So for example, in this specific application, you can see that at peak traffic, we get a recommendation in red that is totally wrong. And by adjusting the rolling window to something that makes more sense for this application, plus adding a safety margin, we can see that we can come up with a better recommendation. So again, like configuring VPA for applications, it might seem simple, and maybe it is for simple applications, but often you need to try and see what it gives, and then finally enable it in prod when you have good settings. The last features that we added in the VPA stack is something that lives in the admission controller that we had to fork. Maybe one day it will make it upstream. At Datadog, we tried to make sure that all changes go through automated safety mechanism in order to avoid propagating a bad change to every failure domain. This means that when we do a deployment, we do it in one zone, then we wait, we look at monitors, and if everything is green, we go to the next. With a default VPA setup, VPA would just like do its thing, update the resource recommendation, and it could break everything globally. So we wanted to make sure that we could apply recommendations safely, reusing the existing safety mechanism that we have. What we did is that we added the trigger mode, which will trigger an apply of recommendation only if it sees an annotation, then promptly remove it. What we do is that we set this annotation in the baseline chart so that when we deploy using the regular deploy stack, it will apply recommendation, but that's it. It will only apply recommendation when we deploy. And because when we deploy, we have all the safeguards, resource changes will be gated by them and should be safe.
Cool. Thanks for that. As you all can see, this involves a lot of fiddling, a lot of changing configuration here and there to make sure that it fits the right service. So as the owner of your service, you're probably the best person to do this type of trial and error fiddling with configuration to find the right fit. Okay, so we are going to move very quickly to Q&A, but before that, we are going to cover something that we also started doing at Datadog, which is multi-dimensional autoscaling, which basically means using horizontal and vertical autoscaling at the same time. And this is something that is definitely not common to do. If you Google for documentation on VPA and HPA, probably you will see some blog posts or even some documentation saying that this is not really recommended. The reason why is kind of tricky, but we really wanted to make this work. So we started doing this, and we are going to explain how we do it, or at least what are we trying. But first of all, Corentin is going to tell us why it's difficult, and it's in some cases even not recommended to do.
Sure. So why do we want to do that first? Then why it's difficult. So why do we want to do that? Why would we use the VPA on something that already has horizontal scaling? The thing with the WPA is that it has a minimum amount of replica, for example, 3. And once you reach it, you cannot go lower. And we noticed that on our smaller deployments in smaller regions, most of the cost was coming from deployments stuck at 3 replicas. Naturally, the solution would be to reduce the size of the pods. But if we do that by hand, as we saw just earlier, that would be an insane amount of work, right? We cannot hand-tweak every services. So we say, okay, we have this thing that can change the size of the pod, so we could use it when the WPA is not enough. The thing is that if you just plug all of them together like that, it's not going to work well. With an A setup, let's say that the CPU usage is increasing, the horizontal autoscaler is going to add more pods. For example, if you go above 65%, then the VPA is going to see, oh, you're using only 65, so I'm going to reduce the vertical size. And the WPA will be like, oh, no, I'm using more than 65. It's going to add more pods. And you will end up in this specific scenario with a large number of small pods because the two systems are not talking to each other and they are trying to achieve different goals. So which goals should we give to the system and to the entire system? What we want is to avoid tiny number of pods, for example, less than 10, because it leads to bigger impact when a pod is lost, and it makes the WPA less efficient when adding and removing a pod, and sometimes totally inefficient. We also want to avoid large number of pods, more than 100, because that leads to increased overhead in the entire stack, and it stresses the Kubernetes control plane that can typically handle only a few thousand pods. We also want to provide a good stability of the vertical size because each vertical change means a totally different profile of the application. Most applications don't run the same way with one CPU or 2 CPUs, and we want to limit oscillations. We want to make sure that the VPA knows about the WPA watermark to make sure that it makes recommendations that take the watermark into account. If my watermarks are between 40 and 60, it means that my target is not 90% utilization. It's between 40 and 60. So how are we solving that? What we did is a VPA post-processor that has access to the number of replica and will restrict scaling based on the current number of replica. If we have less than 10 replica, it's not going to be allowed to reduce the vertical size. The post-processor will just replace the recommendation by the current size. If it has more than 100 replica, it's not going to be able to allow to increase the vertical size. We also bias the recommendation toward the low watermark to make sure that the VPA gives a recommendation that makes sense. And we do use the trigger mode to do that because we need to have access to both the number of replica and the current resource allocation. So that means that we need to have access to the deployment of stateful set. We cannot use the current state of one pod to make these decisions.
Fantastic. Thank you for giving that glimpse of how we're trying to mix and match WPA and VPA. We are going to go for Q&A now. So if you have any questions, we already have a couple of questions in the queue, but if you have any questions and you're in the Zoom, you can use the Q&A button, sorry, and put it there. If you're in LinkedIn, just leave a comment and someone will proxy that one to us. So some just to before the Q&A, some takeaways. Again, we've mentioned this over and over. A lot of tweaking, a lot of fiddling with different settings. It's what it's needed. It's worth the effort, but it's an effort. Also, you need to decide whether you want to do vertical, horizontal, or both. We've also talked about what type of signals you should be looking at and try to stay as simple as possible. And also that you need to think about the whole system, that your application, start with your application, but also the load balancer that you're using, and also whether you're using federal domains and how. So thank you very much. We're going to questions, but if you think solving these problems is interesting, Datadog is hiring, so you can go to our careers page there. And there are openings on the team who is managing all this infrastructure and making this decision, but also a lot of engineering teams who are working on workloads that are using this autoscaling as well. Okay, so I'm going to stop sharing now. And I'm going to start with one question that came in LinkedIn that says, what are the most common case for failure when I see Autoscaler?
I can talk about the horizontal one because we've seen a bunch. And to start with, there is the aspect of the trust you have in the signal you use. So if you're using external metrics, for instance, you want to make sure that you keep in touch with the latency of the data points that you have, as well as ensuring that the whatever contributes to this value, everything is accounted for. So if you're using the CPU average of multiple machines and one is down, that has potentially an impact on the scaling decision. Now, the other thing is in the cluster itself, if you are not using the readiness probe, liveness probes correctly, this could lead to the scaling decision impacting the lifecycle of your application. Say you add more replicas of your workload, which might take a minute to boot up or to be ready. The autoscaler might see that as still requiring more replicas. So you might end up applying more and more and more replicas, but they are not doing their job yet. And I think the last element is really the failure modes. In the WPA, we have a handful of those, but making sure that if you were to cut off all workloads, autoscaling methodology or processes, making sure that this will still be okay and you have monitoring in place for that. So some hints I just thought about.
Good. Corentin, do you want to add anything on the VPA? Things that...
I think the VPA is not really used enough yet to see many failures, but something that could happen is that you don't think enough about the maximum size that VPA can recommend, and you need to make sure that the maximum size matches the maximum size of the nodes that you have. If you set the maximum size to, let's say, like 100 CPUs, but you only have backing nodes of 20 CPUs, you're never going to schedule your pods. So you still need, it's automatic, but you still need to understand how it works end to end.
Sounds good. Thank you. Question that came here in Zoom. How do the autoscaling strategies differ when you're talking about offline workloads like Spark, model training, etc.?
I can talk about one offline workload that I worked on, which is reloading of an archive. It's something that is not really online because we had an archive, we want to reload it, but it's not exactly like data. What we have though is that we want to reload it in a given time. We say, okay, 1 terabyte, we want that to take 10 minutes. And we kind of know the throughput that we can have. So from that, we have a goal, we have a throughput, we can derive the amount of resources that we should get it. So it's, in a way, it's auto-scaling because we scale the job when it starts with the number of pods that it should get to achieve its goal, right? It's SLO. So that's one of the things we do. And the thing is that if you don't have a goal in terms of completion, you don't know how many pods you should give it. If it can last a year, then don't use autoscaling, give it a single pod and wait.
That's a very good point. Another question that came in the Zoom, there is a way to build SLOs that measure how many times you are scaling up and down for any Kubernetes workload.
So for the WPA, we instrument with a lot of telemetry and we drive our SLO. So we have sort of a controller SLO, which is we need to process all the WPAs within 10 seconds, which is good because we have a reconciliation loop of 15 seconds. But on top of that, we have models or templates that application teams can use for their own scaling events, and using audit logs as well as the logs that are generated by the controller, we give them the tools so that they can set up whatever is relevant to them.
Good. Another question from LinkedIn. How do you manage log retention when doing autoscaling?
So, if I understand the question correctly, if the question is, how do we keep logs when adding and removing replicas, then the answer is easy. We send the logs to Datadog and we have them. If the question is, how does the log backend keep the logs when adding and removing replica? Because it needs to keep them. So in other words, how do we deal with autoscaling of stateful applications? Most of the time, what we do is that before removing a pod, we will move the data to the other ones, and only then we'll allow to the pod to go away. And this is something that is kind of hard to do with the WPA. So often for stateful applications, we don't use the WPA. Instead, we have a dedicated controller for this stateful application that will do many things, including, for example, auto replacement of instances, but also autoscaling. Also for databases, most of the time, it's not only CPU, but you want to look at it's many, many things. So it's better to be close to the application, and it's only close to the application that you will know if you need one more replica, if it's okay to remove one, that kind of thing.
Sounds good, and good point. Always being close to the application, understand how your application behaves. Okay, I think that was the last question that we had both on LinkedIn and Zoom. So thanks everyone for joining. Thanks for the questions. And of course, thanks Corentin and Charly for sharing all that knowledge. And I'll see you on the next episode.